Okay, thank you. Well, thank you for organizing such a nice event here and for inviting me. I hope you can hear me. This is just for the camera, so I hope you can hear me. So I want to tell you about some progress in integer programming over the last several years, and over the last year or two, this had found some nice applications in parameterized complexity. So this is why I'm talking about this here. So I hope you can see. Also, it's a bit small, so we are talking about integer programming. I hope this is visible. Integer programming. So this is a very, I think everybody knows what integer programming is. It's an optimization problem. We are minimizing or maximizing an objective function, f of x, over integer variables. So we have a vector x of integer variables in dimension n. N-dimensional vector of variables, and each coordinate should be integer. So this is why this is integer programming. And we have a system of linear inequalities, so a matrix ax less than or equal to b, and upper and lower bound on the variables. And I can assume all the data is integer. Otherwise, if it's rational, you can scale it. So the data is integer, a, b, l, u. And also, let's assume that the lower and upper bounds are integers, so things are bounded, but this is not really crucial. Some of the variables may be unbounded. So this is the problem we are talking about. And, well, it has generic modeling power. It's very easy to write down any discrete optimization problem as an integer program. But it is NP-hard already for linear objectives. By the way, if you have any question at any point, stop me if you don't see anything or... Okay, so it's well known to be NP-hard. So what can we do? Well, first of all, there is this classical theory of fixed dimension. So if the dimension n is fixed, then there's a classical theory from the early 80s of the last century by Lenstra. You can solve it in polynomial time. And in fact, if the dimension is a parameter, it is also fixed parameter tractable. So this is a very useful theory, and it's well known. And I'm not going to talk about this at all here. You can find this in books. And so far, almost all applications of integer programming to parameterized complexity and also to approximation algorithm use this theory. So this is very useful. But it has some limitations because the number of variables is not variable. It's a constant or a parameter. So here I'm going to talk about a new theory. And the dimension is always going to be variable, so this n is going to be large, hundreds, thousands, variable dimension. And this new theory enables to solve still broad and natural classes of integer programs. I'll give some applications, and as I said, there are other applications that came up over the last year or two. And this class of program is also universal in a certain sense. There is another parameterization hidden here. You will see it later. And every integer program falls into one of these classes. So it is universal also for integer programming. And as said, there have been recently several applications of this theory to parameterized complexity. It's picking up last year or two. And very recently I came across also a very beautiful first application to approximation algorithms. Okay, so the plan is the following. We have 50 minutes, right? We started at 10 to... So 2 lectures. So the first lecture, I'm going to tell you what is this? What is this?
Move the mouse. Move the mouse.
Move the mouse. Ah, thanks. No mouse. So I'm going to tell you first of all about what Graver bases are. So this is the main engine, the main definition in this talk and the main engine of this theory, Graver bases, and what they can do for integer programming. Then I'll briefly introduce the most fundamental, I would say, class of programs where this theory works. So this is called n-fold integer programming. Most of the lecture will deal with this. There are generalization of this class of programs. There are various generalization extension. I'll mention some of them in the end. But this is perhaps the most easy to explain, and also already this class is universal for integer programming. So here I will just, in this first lecture, I'll just briefly introduce this and state the main result, and we'll take a closer look on this in the second lecture, and then some examples. So I'll discuss multidimensional tables. This is a generic example of such a class of programs, and this is also universal for integer programming. Second lecture, we'll take a closer look on this n-fold IP and show that it is fixed parameter tractable. So this will be most of the second lecture. And then I'll talk about another application closely related to tables, multi-commodity flows, and the huge or high multiplicity version of this, which is something I've been looking on recently. And this huge version of problem is something which has been considered in other contexts. And then some other applications, briefly, extension and directions. Okay, so let's start with Graver bases. For this lecture, the first lecture only, you can find the background in my book here. So the book is available electronically as a PDF file from my homepage with permission of the publisher, so you can feel free to download it and take a closer look on this theory. So this is good for this talk. In the first talk, I basically cover things that are there. The second talk is not covered in the book because it's material that appeared later than the book. So what are Graver bases? Here is the basic definition of this lecture, and these two lectures actually. It's a very simple definition actually, but it very quickly leads to deep things. And so you start with an integer matrix A, an m by n integer matrix, and you look on n-dimensional vectors in the kernel. So you look on integer n-dimensional vector x, so that ax equals 0. They are integer and non-zero. And among those vectors, you have infinitely many such vectors. Among those, in each orthant of the space separately, you take those which are closest to the origin. This is the Graver basis geometrically. So again, you look on the vectors in the kernel of the matrix, the integer non-zero vectors. There are many of them, infinitely many. In each orthant separately, you look on those which are closest to the origin. And formally, there is a partial order here, which is called conformality. So x is conformal or less than or equal to y if they are in the same orthant. So they have the same sign on every coordinate. They are sign compatible. And x is closer to y to the origin, so on every coordinate, the absolute value here is less than this. So this is the Graver basis. Very simple definition, but it's a very complicated object. It's very hard to compute, and if you take even a small matrix, immediately you get very fascinating and hard to understand structure. You will have interesting vectors. Let me give you a quick example here. So suppose we have this simple one-row matrix. So the Graver basis consists of three-dimensional vectors in the kernel. So first of all, you will have those of minimal support. So those of minimal support. So these are the so-called circuits. You see that, of course, each one is in the kernel of this matrix. The inner product is 0. And they're called circuits. They have minimal support. So if you have a larger matrix, those corresponds to the supports of such circuits correspond to sets of vectors which are minimally linearly independent. So the supports are the circuits of the matroid of the matrix. This is why they are called circuits. And so these you always will have the circuits in the Graver basis, but you may need more. So in this example, you also need this vector 1 minus 1, 1, which is not a circuit. And you can check that it's not above any of the other vectors in this conformal order. Okay? Now, already for this small example, and in general you have many more non-circuit than circuit. You have much more non-circuits. Now, already in this example, if I ask you, is this the Graver basis? Yes?
What do you mean by circuit?
So I said circuit is a vector whose support correspond to a set of columns of the matrix, which are minimally linearly dependent. And you scale it so that it's still integer and the entries are relatively prime. These are the circuit. You have at most n choose m such elements. But the non-circuits, you may have many elements, and the number of elements may depend on the entries of A also, not only on the dimensions. So already here, if I ask you, is this the Graver basis or you need more elements, then you'll have to think, it will take you some time to figure out that this really is the Graver basis. So this is one open problem, Graver basis detection. I give you a set and a matrix. Is this the entire Graver basis? Okay, so this is the definition. Now, why are we interested in Graver bases? So if we have the Graver basis, we can do integer programming, basically. That's the message I want to give you now. So I'm going to give you 7 theorems. Here's the first one. So this is linear integer programming. This is the classical integer programming problem, linear objective function w dot x. And of course, it's NP-hard. The dimension is variable, very large dimension, variable part of the input. It's NP-hard. But for the time being, I assume that I have the Graver basis of A as part of my input. I have an explicit list of the vectors in the Graver basis. Later, we will see how we get the Graver basis. But for now, I assume I have it. And then the theorem says we can do it in polynomial time. And no. In the input, which includes the bit size of the numerical data, which is the bit size of L, U, B, W, and A. This could be given in binary, but also of the Graver basis.
Which could be much larger?
Yeah, it could be much larger. Later, we'll see how to get it directly from the more natural data. But for the time being, I assume I have it. And the next theorems, so this is the beginning of this theory. This is the first paper on this theory. And I'll give you some more theorems. Later, we'll prove this theorem. I'll sketch the proof of this theorem. But I'll give you more theorem, and everything is going to be the same. By the way, I'm assuming now standard form. So this is no loss of generality. I assume I have equations here. So AX equals B always. It's more convenient to work in this way. And all the inequalities are in the upper and lower bound. If you have inequalities, you can add slack variables and force them to be non-negative. That's a standard trick. So this is no loss of generality, and it's more convenient. And in the next theorem, everything is going to be the same except for the objective function, which will change. So here's the next theorem, a generalization of this.
Sorry, before going through, can you go back to the definition, the conformal minimal? Because I think I didn't digest this definition yet.
X is less than or equal to y if they're in the same orthant. They're compatible in the sign on every coordinate, and X is closer to y to the origin.
So this is for conformal, but when you say
okay.
set GA of conformal,
Let me maybe one thing. This is a well order. So every set of integer points have a finite set of unique finite set of minimal points under this order. And in particular, if I take the set of all non-zero vectors in the kernel, it has a unique finite set of minimal elements in this order, and this is the Graver basis. Okay. Yeah, thank you. This is yes, which are non-zero, because if I put 0, 0 will be the only one. Yeah, thanks. I should have said that. Okay, so the next theorem is separable convex. Again, I assume I have the Graver basis, but now the objective is more general. It's univariate, sum of univariate convex functions. So this includes linear as a special case. This is a convex function of certain type. It's very useful. It includes linear objectives and includes norms and all sorts of other things. And I should already say that even the Graver basis has limitations. So you cannot hope to put here an arbitrary convex function. Okay, so minimizing an arbitrary convex function, not separable, even if you have the Graver basis, this is NP-hard. So there are limitations. But this can be done. So this is the second theorem. Let me go over one more theorem, and the others I'll do faster. So here is the previous theorem, we could minimize some convex function. Here I can maximize some convex function. And they are of this form, FWX. So now W is a D by N matrix. I have a D by N matrix. Each row of the matrix WI gives me a linear form. So each row gives me a linear objective. If I take a feasible solution X and multiply by WI, I get its value under one criterion. And if I multiply X by W, I get a d-dimensional vector where the ith coordinate is the value or the utility of the solution x in criterion I. And then I weigh together by this convex function. I want to maximize the balanced utility. So this also can be done in polynomial time using the Graver basis. Here, it's very unlikely that you can make it FPT if this is the parameter. It's probably, I don't know, W1 hard, or it's probably not going to be FPT. And this uses, this combines Graver basis and another theory which I developed in the past with Uriel Rothblum. I'm not going to discuss this in the talk beyond this slide. Then there are other theorems, so you can find a point of minimum norm or a point closest to a given point. This is a special case of the separable convex theorem. You can do some quadratic minimization. You can minimize some quadratic functions, but not all of them, of course. The quadratic function should lie in some restricted cone. So this is somewhat restricted, but you can do some quadratic programming. And this extends to polynomials. Again, there is a cone of multivariate polynomials of degree d, which you can minimize in polynomial time using the Graver basis. And you can also do some robust optimization. So robust, well, again, just to make sure you are following, again, the setup is, this is an integer program, variable dimension, standard form. So in general, this is NP-hard, but we have the Graver basis as part of the input. And now the objective is this robust thing. So in robust optimization, some of the data is uncertain. You have uncertainty. And here you have uncertainty in the cost. So the cost Ci of variable xi lies in an interval between di and ei, and you don't know what the cost is. So you have an adversary. You choose an x, and then the adversary chooses the worst cost, and you want to minimize. So you can do this. And this is just one first step in studying robustness with Graver bases. So you can, this is, I think, an open, interesting area to see what other robust optimization problem you can do with the Graver basis. Maybe the B and the L and U changes in an interval or something like this. So I don't know what can be done there. Okay, let me do one proof here. So the main proof. The main proof is linear optimization and separable convex. It's basically the same proof. So theorems 1 and 2. So we want to minimize a separable convex function or a linear function given the Graver basis. The yellow points are the integer points. So this picture here, I don't know if you see this. The yellow points represent the feasible solution. This is the integer hull, the convex hull of them, but you don't have access to this because you just have access to this weak blue. I hope you see this weak blue. These are the inequalities, the relaxation. You don't see the integer hull. You see it after you can do linear optimization, then you see it because there's equivalence of separation optimization, but that's not for this talk. So the idea is this is an iterative algorithm. First of all, we have to find an initial feasible point, or decide that there is no point here, this green point. This is done by an auxiliary program, which you set an auxiliary program, and then you have an artificial initial feasible point, and you optimize an artificial objective function, and you basically do the same thing that I'll describe now for optimization. So I'm not going to explain this in detail, but you can find an initial point, and then you keep doing iteration where you improve the point. So you choose steps. Here is one step. You move from one feasible point to a better one, and you improve by what we call Graver best step. So Graver best step is something very important that will be discussed in much more detail in the second lecture. This is very important. What is a Graver best step? It's a step, this step, the vector that you add to the current point, which is an integer multiple of some vector in the Graver basis. And it should be a step, which is an integer multiple of an element in the Graver basis, which stays feasible when you move, and gives you the best possible improvement among all such steps. Is this clear? I mean, this is, yes.
Does the initial point need to be integer, or can it be?
Yeah, integer. Finding the initial point is not easy, but it's done by the same way that you do optimization, which I'm explaining now. It's not easy.
It also makes use of.
It uses the Graver basis. It also uses the same Graver basis. So it's a procedure, but the complexity is about the same as the optimization once you have the feasible points. I'm not going to do it twice, but it's not easy, of course. It's as hard as integer programming.
What is the link between CZ and the initial point?
No, CZ is the step. The initial point is x. You add to it x plus CZ, you move through here. It's the step. It's the blue arrow, the vector. What I want to point out now is, look, the Graver basis vectors here are in the kernel of the matrix. So A times Z is 0. So if you add multiples of Graver basis elements to feasible point, you do not change the right-hand side. Okay? So you just have to make sure you don't violate the upper and lower bounds. And the way this is done here now is very simple, because at each iteration you have the Graver basis. So how do you do it? You take every vector in the Graver basis one by one. For each one, you have to find the best step. The best step becomes a univariate convex minimization problem, and you do it by binary search, basically. So if you have the Graver basis explicitly, then you can find the Graver best step easily. But later we will see that we can do it without actually having the Graver basis. So for this algorithm, it's actually enough that I have an oracle. I don't want to talk about oracle, but it's enough that I have an oracle that I ask him and he gives me the best Graver best step. And if you keep using Graver best step, you converge in polynomial time. And I'll explain this in the next slide. So there's something called integer Cardioid theorem, which is used, and the structure, the separable convex structure of F. And this will guarantee that you can converge in polynomial time. So I want to sketch this polynomial convergence, a bound on the number of iterations, yes.
So when you say polynomial time, what is it?
So again, polynomial, for the time being, polynomial means my input are all these numerical things, A, B, L, U, and F, presented somehow, the binary encoding, so they can be large numbers, and the Graver basis.
So the number of vectors on the Graver basis, or again the number of vectors and the bit size?
Well, actually, the number of iteration is not going to depend on the Graver basis is needed here. So if I have an oracle, this is 1, this counts as 1. So the number of iteration, well, I'm going to say the number of iteration is going to be n times the bit size of the other stuff without depending on the Graver basis. So I'll do it on the next slide. So the number of iteration is independent of the size of the Graver basis.
Do you know that the distance is polynomial
The distance,
to where you want to go?
well, it's going to follow from this proof here, from the proof. I don't know it ahead of time. But the distance, you mean the number of steps. That's exactly what's going to be proved. So let me give you the proof and the statement of the exact bound, and then I think maybe this will be clearer. And I'm going to, it's simpler to do it for linear objectives and maximization, so I'm now maximizing a linear objective. A slightly more complicated argument work for separable convex function. So I'm maximizing this Wx. And let me tell you what is the integer Cardioid theorem. So what is the integer Cardioid theorem? It tells you, look on an integer vector in the kernel of the matrix. Ax equals 0. Okay? You can write it as a sum, x, sum of summands ci, zi, each one is a integer multiple of elements in the Graver basis. So you can always take any vector in the kernel, write it as a sum of some integer multiples of Graver basis elements. Okay? But the sum is, first of all, the sum is conformal. This means, so the sum is conformal, this means that each summand is in the same orthant as x, and they're all in the same orthant. So all the summands and x agree on the sign of every coordinate. So basically, you can write X by taking vectors in the same orthant. And this part that you can do a conformal sum, this is basically the definition of the Graver basis. This is really the motivation for the definition of the Graver basis, that you will be able to write every vector in the kernel as a conformal sum of multiples of elements. So this follows immediately from the definition of the Graver basis. What is more tricky is the bound on the number of summons. So the Graver basis can be very large. So the cardinality of the Graver basis may be exponential in n. It may depend on the binary encoding of the matrix A on the entries. It can be very large. So offhand, maybe you need in the sum all of them. But this tells you need linearly many. And in fact, for our purpose, it was enough that we had a polynomial bound. Any polynomial in terms of n bound on P would be good enough. But this is what is known. The proof is actually quite tricky. If there's a weaker bound 2n minus 1, that's already tricky and a very nice proof. The 2n minus 2 is a paper of 40 pages to get it down from 2n minus 1 to 2n minus 2. So that's not a big deal, but the motivation was that for many years there was a conjecture that you can actually put n there. N like in the usual real Kara-Theodori theorem. And a few years ago, this conjecture was disproved, so there is a lower bound. I mean, you cannot put here a bound which is better than 7 over 6n, and this is, there's a counterexample which uses some methods from algebraic geometry, so it's quite complicated. So the best bound there is not known. But for us, it's enough that it's polynomial. And now what does it help us? So we are solving this using the iterative so we are using this iterative procedure that I had before. I'm moving from one feasible point to another using Graver best step. Okay? And so suppose xk is a point at some of these iterations, some iteration, and it's not optimal, and let x star be an optimal point. Okay? Now look on the difference, x star minus xk. I'm trying to figure out with time here, 20 is half an hour. Should probably speed up a little bit. So look on the difference. The difference is in the kernel of A because both points are feasible, so they both satisfy Ax equals B. So the difference is in the kernel. So you can write it down as such a conformal sum. Okay? And now we look on the gap in the objective function between the optimal one and the current one. This is the gap. It's positive. And you can write it, then it's the sum of W times these summands. And so at least one of these summands will give you an improvement, which is at least as the average. Okay, at least one of these summands will give you an improvement, which is at least as much as the average improvement of this difference. And now, okay, so among these p sums, one of them will give you good improvement. And now I'm claiming the current point plus Ci. Zi is also feasible because the sum is conformal. This is where we use the conformal sum. And the reason is because if you look here, move xk to this side, so you see that x star, the optimal point is xk plus sum of the sum of the summands. But xk and x star, they are both feasible, and the difference uses only vectors with the same sign on every coordinate. So if you just take any subset of the sum and add it to xk, you stay feasible. You don't violate the bounds.
The CIs are positive.
Yeah, so you can assume that that's not important because the Graver basis is symmetric. If a vector is in the Graver basis, then minus the vector is also in the Graver basis. So then you can, so for this analysis, yeah, maybe I should, maybe for this analysis I should say that they are positive, yeah. Yeah, good point.
So the CIs are positive.
The CI are positive, yeah. The Zi are elements of the Graver basis.
And they are in the same order.
Yes, they are in the same order, but the conformal sum, I assume that this entire thing is in the Graver basis, is conformal. You see, not the Zi, but Ci times Zi is in conformal. You see, that's what but alternatively you can say, let's force this to be non-negative and then this should be in there. But I just said that the sum in itself, including the coefficient, is conformal. But again, that's not so important because if G is in the Graver basis, minus G is also there, always. But maybe it's better to present it that the CI are non-negative integers and so this is going to be feasible for any partial sum here. And but now, so one point here, you see this sum, we don't know this sum. We don't see this. We don't know the optimal solution. If you knew the optimal solution, then I'm done. I just know that there exists such a sum. I don't know the optimal solution. I don't know CI ZI. I don't know it. But what I do know is a greater best step, which is better than this. That's the point. So if CZ is a greater best step, which I found by looking on the entire greater basis or by some oracle, then it gives you a better improvement, at least as good as improvement than this. Our algorithm set the new point in the new iteration xk plus 1 to be xk plus the greater best step, which is something we can get. And so if I compare now the gap from the optimal objective to the objective of the next point in the next iteration, then it's this. And this is less than or equal to what I could do with the best improvement for one of these summands, and then you just plug in this inequality and you get this inequality. So this is basically this is the most technical part of this first lecture. So if I summarize what I showed you is the following. The gap we're maximizing. The gap in the objective function in the next iteration is less than or equal a constant fraction of the gap in the current iteration. So when I do this iteration, I keep shrinking the gap by a constant factor. And since everything is integer, the W is integer, X is integer, this is an integer number, when I'm below 1, this is optimal solution. And this leads to if you just do some computation, this leads to this bound. So this clarifies, I think, your question now. So the number of iteration is bounded by n, linear in n, the dimension, and L is the bit size of this. So it behaves nicely. You know, that's important. So these could be very large numbers, like 2 to the n, and this still works. And in fact, very recently, we show with Asaf Levin and Martin Kutechki. I'll mention Martin later also in the second part. He's here. We show that, in fact, you can bound the number of iteration. It's strongly polynomial, depends only on n, without being dependent on the bit size. Okay, so this completes this proof, and I'm going to skip this geometric, this multi-criteria. This is a nice geometric theory, but I'm not going to discuss this here. Okay, so this is very nice, but I assume that I have the greater basis. And if you take an arbitrary matrix and compute it, it's going to be exponential, and you cannot compute it. So where do I take the greater basis from? So there are several important and interesting classes where you can do that, and I'm going to talk about n-fold integer programming. This is the fundamental and perhaps easiest class to understand. And in this talk, I'll just give you 2 slides defining the problem, defining the setup, and the main theorem. And we'll take a closer look on this later on and show that you can solve it in fixed parameter tractable time.
You are talking about greater basis. Can you give us some easy example of?
I gave you 1-to-1.
Okay.
It's easy. But even this example is not so easy. If I have to ask you, go ahead and compute it and convince that what I gave you is the greater base, it will take you 15 minutes, I think, at least. So it's a good exercise. Maybe I should give another example for you. If you know what totally unimodular matrix is, for totally unimodular matrices, the greater basis consists precisely of the circuits. And the circuits are 0, -1, 1 vectors. So this is a nice example where you have really understand the greater basis. Very special. Okay, so what is an n-fold program? So an n-fold program is simply an integer program defined by such a matrix. That's the definition. And the definition of this matrix is also quite simple. You start with what I call a bimatrix, RS by T bimatrix, so a matrix A, which has 2 blocks. Both have T columns, This has R rows, this has S rows. Okay? I call this a bimatrix, and then you give me n, large n, and I construct this big matrix, which has blocks, A1, n times A1 blocks here, and n blocks of A2 on the diagonal, and the rest are zeros. And integer programs are defined by such matrices. The number of columns here is n times t. Okay? N times t, t for each block. And so the variables in such a program, the vector x of variable will have nt variables. And we arrange them in n pieces, we call them bricks, n bricks of size t each corresponding to these blocks. So in an L-fold program, the vector of variables consists of n bricks. Each brick is in dimension t. T is fixed or a parameter. It's going to be a parameter later. Let's now suppose this is fixed, and n is given as input. So let's assume this is fixed. Later, this is going to be a parameter in the second lecture. So this is fixed. And now the basic lemma here, which I'll sketch some of the proof later again in the second lecture. The greater basis of such a matrix can be computed in polynomial time. Let's say for fixed A. For fixed bimatrix A, the only input for this computation is n, and I can compute the greater basis in time order n to the GA, where G of A is something called the greater complexity of the bimatrix A. So every bimatrix, every matrix, such matrix with two blocks, have a certain non-negative integer called the greater complexity, G of A. It's very hard to compute, and it's very interesting. We'll talk more about this in the second lecture. I'll give you some examples. But for now, I am just saying that if that I can compute the greater basis in polynomial time, n to the G of A, this greater complexity. And in fact, the cardinality of the greater basis may be this big. So you cannot avoid this. The cardinality of the greater basis may be n to the G of A. And if you think about this as a parameter, this is not fixed parameter tractable. That's our problem. And we are going to fix that in the second lecture. And so if you can compute the greater basis, then you can apply all the theorems I had before and get and solve integer programming. So this is the main theorem on n-fold programming, and we are going to give more details on this later. We are solving an integer program, lower and upper bounds. The vector of variables has, we have n times t variables, so variable dimension, large dimension, nt. The objective can be any one of those objectives I mentioned before on theorems 1 through 7. And the only thing which prevents this to be NP-hard is that the matrix here is an n-fold product of a small bimatrix. And then we can solve it in order n to the GA times the bit size of the numerical part of the data.
So your matrix A is an integer value, right?
Yeah.
But you don't know if it's non-negative.
No. It could be, just integer. Could have negative entries. And the proof I said, you use the lemma to construct in polynomial time the greater basis, and then use it in the iterative algorithm or other methods that I need for the other theorem. Okay, so let me give you one example, the generic example of this class. Time is running short. So this is one of my favorite problems, and there's still lots of work to be done on this table problem. So such tables have been studied by in many communities, in statistics, privacy, databases. They are very useful. Let's look on three-dimensional tables. So three-dimensional, this is a 3 by 4 by 6 table. And table, I mean that each cube here is a variable, which would be non-negative integer. And I'm looking for such tables, non-negative integer tables, where the sum on each line is a prescribed number. I've given some, you see the numbers here should sum to 6. 1 plus 0 plus 2 plus 3 should be 6. The same in this direction, the same in this direction. And I'm giving all the line sums from all directions. So many of them. And this is, of course, an integer program. Yes, it's the set of integer L by M by N arrays, triply indexed variables, non-negative integer, and whenever I sum on one of the indices, this is a line, it should equal some given number. This is my input. So my input are these numbers given in binary, large numbers, and the LMN, the dimensions. And let's consider the complexity of the decision problem here. Is there a table of these line sums? Just the decision problem. So here I'm looking on 4 situations here. 4 situations depending on which sides are fixed and which are variable. Okay? And obviously the top is harder than the bottom. So if anything is interesting here, what's the complexity here? What should be the complexity here? LMN are variable. I mean, the table is 1,000 by 1,000 by 1,000. This is variable part of the input. This should be NP complete. Otherwise, it's completely boring. And down below, when they're all fixed, should be polynomial time. So indeed, this is NP complete. This is a result of Irving and Jerome, Mark Jerome. You can reduce 3-dimensional matching. It's more complicated than 3-dimensional matching because 3-dimensional matching is an n by n table. And you require line sums which are all 1, but some of the entries may be forced to be 0. That's your input. And here, not. I cannot force the entries to be 0. The entries are all free. Only the line sum force them. So it's a bit tricky to do this reduction. If I go down to LMN fixed, let's say like this table, 3 by 4 by 6. You fix the 3 by 4 by 6. You have, how many variables you have now? 3 by 4 by 6. 3 times 4 times 6, 72 variables always. So here LMN. So how can I solve this in polynomial time? Use Lenstra's algorithm. Integer programming in fixed dimension. Because if they are fixed, the dimension is LMN. Fixed dimension L times M times N. You can use Lenstra's classical fixed dimension theory and solve it in polynomial time. But you see that even for such fixed tables, often you need Lenstra's algorithm, which is a complicated algorithm. So this will be Lenstra in 72 variables. The input for this table will be just these green numbers, many of them, 12 from here, 18 from here, and so on. They're given in binary, large number. And often I need Lenstra's algorithm. Even for 3 by 3 by 3 tables, by the way, this is the first situation where I don't know a simpler algorithm. 3 by 3 by 3 table, you have 9 line sums from here, 9 from here, 9 from here. So you get 27 numbers, large numbers, and you want to decide if there is a table. So here is one question for you. Is there a simple algorithm for 3 by 3 by 3 by tables without Lenstra? But we want to do better, so let's look on these other situations here. L fixed and Mn variable. Now 2 sides are variable and L fixed, so here turns out this is hard, and it's in fact universal for integer programming. So this is I have a result with Jesus de Loera that even if one side is 3, like here, 3 by m by n, so narrow tables, 3 layers, and m by n. So not only this is NP complete, but it's universal. If you take any integer program, you can embed it in such a table program isomorphically. So in such a way that there's a bijection between your integer points and the table, the feasible tables, and also the real points and the real tables. So even the polytopes are the same. So this is every polytope is such a polytope. So so this is why I think tables are very important and very interesting, because they're universal. And now, what about this other case here? I mean, this was the large. Actually, chronologically, this is how it happened, I think. Yeah, actually, maybe this was before this. But how can we? What about this? So these are long tables. L by m by n. Let's say 3 by 4 by n. So a long table. What?
It's a fixed rank, right? If you write an integer program. So if you write an integer program, that will be a fixed rank.
No, it's not fixed because you have n. Now n is variable, so the number of variables is L times n times n. The fixed rank was down there, so now it's not fixed. You have a variable number of variables. Well, there's a hint here. You have n, red n, so that's an n-fold IP. This was the motivation for this entire theory. Started from this problem here. We wanted to solve this problem, and this is how this theory started. So this is an n-fold program. So I want to finish this lecture by. So I have, how much do I have? 5 minutes. try to explain why this is an n-fold program. And this holds for tables in more arbitrary dimension, m1 by m2 by mk by n. So any dimension, as long as all the sides are fixed, let's say fixed or parameters, and one side is long and variable. The number of variables is variable. It's m1 times m2 times mk times n. And now I'm back to optimization. I want to optimize over such tables. This is a classical problem of Motzkin. And I'm claiming this is an n-fold program for whatever function you want. Non-negative integer are the tables. And I'm claiming you can write a suitable bimatrix A, which depends only on the fixed sides, m1, mk, so that when you write this system of equations with the n-fold product, this will be the line sums. And the way this is done, so this holds for margins more generally. Margins are also, you can do plane sums, hyperplane sums, things like that. But let's talk about lines. So look on this table. These are fixed, and one side is long. And now you see the bricks or the pieces, the t-dimensional pieces correspond to layers, like this. You see, this is the indexation. So if I look on 3 by 4 by n tables like in this picture, my t, the number of columns of the bimatrix is 12. Right? Each layer has 12 entries here, 4 by 3. So these are my layers, and I have n of them. Layer, 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 layer. Now, if I look on these equations, there are two types of equations. There are these equations which involve A2. You see, A2 times a brick should equal something on the right-hand side. This is part of this system of equations. Okay? The system of equations here, you multiply this with x on this side, and each brick, each layer in this table example is multiplied by A2 and should equal something. So you can set A2 to give you the line sums on one layer. These are just the row sums and column sums. So A2 gives equation of margin or line sums summing within a single layer at a time. One for each of those. They all have the same system. You see, they all have the same matrix. But each brick, each layer is multiplied by A2 separately and should equal the line sums of this brick. And if you look on the line sums from this direction, the vertical ones, think about A1 as being an identity. This is true for line sums. So for line sums, A1 is the identity. And then this part of the system of equation tells you that you basically sum all the bricks and multiply by A1. So if A1 is the identity, this part of the system tells you, take this layer plus this, plus this, plus this, sum them all up, and this should be equal some right-hand side, and the right-hand side here would be a 12, a matrix, 4 by 3 matrix, which gives you the line sum from here, the vertical line sums. So A1 encodes the vertical line sum. So this gives you some flavor of the modeling power of this n-fold programming, and for table it works very naturally. And so a corollary, I'm almost done with this first lecture. A corollary of all this theory now is for tables that you can optimize, solve such table problem, linear or nonlinear optimization over M1 by M2 by MK by N tables in polynomial time, order n, gm1 mkl, where g, what is g? gm1 mk. This is what I call the Graver complexity. The Graver complexity was defined for a bimatrix, but the bimatrix for the tables just depends on these numbers, m1, mk. So now this Graver complexity depends only on these other dimensions. And so we can solve it in polynomial time, but not in fixed parameter time. Because if the mi's are the parameters for this problem, then they appear in the exponent here. And this is something we want to fix in the next lecture. Let me just, this is almost the last slide. If I go back to three-dimensional tables, I said that we have universality. 3 by m by n tables with given line sums are universal. Every integer program is one of those. And here you can see a natural parameterization of tables. Let's say three-dimensional tables and integer programming. This m, the width of the table, is a natural parameter. So for 3 by n tables which are universal, n is variable, that's the length. The width m is a parameter. And we get a parameterization, then we will have here g of m. So the complexity will be n to the g of m times L. But this is not FPT, it's polynomial for fixed m, and we want to make it FPT. So that's what we are going to make in the second lecture. So that's it.